Okay, so hello everyone. This is the second part of MAC protocols. In this video, we will cover CSMA, CSMA CD, and CSMA CA. What are these? Carrier sense multiple access collision detection and collision avoidance. Okay, so in this video, we will discuss about CSMA, and in this CSMA, we will discuss 0, 1, and P persistent CSMA, and then we will discuss CSMA CD and CSMA CA. So, what are the keywords related to this topic? Transmission time, propagation time, and vulnerable time. What is transmission time? In simple terms, when we are transmitting bits on the communication link or the channel, that time is transmission time. And propagation time, from sender to receiver, bits are propagating on the link or channel, this time is propagation time. Vulnerable time, the length of time in which there is a possibility of collision, this is vulnerable time. So these are the keywords related to this topic. Now we are going to discuss CSMA, that is carrier sense multiple access. Okay, in the MAC layer after ALOA we have the next protocol, which is CSMA. Okay, and this is the most important protocol, carrier sense multiple access. Multiple access means the same thing we discussed before. Okay, we are talking about shared mode. Shared medium means our channel is shared. Okay, this means multiple nodes shared in the same channel. Okay, now when I have to transmit some data, let's say node A want to transmit data. In pure ALOA and slotted ALOA, we generally said that you can transmit data directly, but here we have an important concept called carrier sense. This means before data transmission, the important step you have to do is to sense the carrier. What does this mean? The data you have to send, you keep it on hold. First, your transmitter, the node you are connected to, your transmitter will check the common medium, will sense it to see whether the some data is already moving or not. In other words, it checks if some frequency or signal is already going through the medium or not. Okay, if a signal is already moving, then it means the medium is busy. So if your medium or channel is busy, then you hold your data. If you also transmit at that time, what will happen? Obviously collision will occur, and if collision occurs, then your bandwidth will be wasted, so the throughput will be go down. This is the basic concept here. When any node in a system wants to start transmission, before starting transmission it will sense the carrier. Okay, now an important point here where students get confused. Sensing the carrier doesn't mean that it will sense the entire channel or entire medium. No, that's not how it works. Let's say our medium is 500-meter long. Okay, our wire is 500-meter long, half a kilometer we can say, and it has multiple nodes connected to it. Let's say 4 nodes are connected. So if node A want to send data, when A senses, it will sense only at its point. Okay, it will only check at its location, is data already moving or not, is there already a signal present or not. If a signal is already there, then A will not transmit data. But student get confused that thinking that it will sense the entire channel. No, it doesn't work that way. Okay, if data is already moving somewhere else in the channel, it will not reach you immediately because of propagation delay. Okay, some other node might have already transmitted data, but that signal has not yet reached your location, so in that case you will not come to know about it. Okay, this is important points. To sense the carrier means you won't sense the entire path, only your local area. Think of it like you are standing in your house and you only check if any vehicle is moving in front of your house door or not. You can't check the vehicles on the whole street. Okay, when the vehicle comes in front of your house, only then will you know that there is a vehicle already present. Okay, and then you don't bring your car out. This is exactly the concept of carrier sense. Okay, now CSMA has different variations: 1 persistent, 0 persistent, and P persistent. Let me explain each one by one. Okay, 1 persistence means what? Let's say we have 4 nodes connected to our medium. In 1 persistent CSMA, if node A has to transmit data, A already has data ready to send, but it will first sense if a signal is already moving or not. If no signal is moving, then A will immediately transmit that data. Okay, simple concept. If it detects that medium is idle, nothing is moving, then A will immediately transmit its data. But if A senses that a signal is already moving on the medium, then A will not transmit its data immediately. Okay, so this is the concept of 1 persistent. Generally the concept of Ethernet works on this principle. Okay, there are high chances of collision here. Why? Because in the worst case, when all nodes detects the medium is free, then they immediately transmit their data simultaneously. Okay, then there will be a collision. Now next we have 0 persistence CSMA. In 0 persistence CSMA, when a node checks the medium, if the medium is idle, then it will immediately transmit its data, same as before. But if node A checks that the medium is busy, or finds that a signal is already moving, meaning if the medium is busy, then what will A do? It will wait for some random amount of time. This random amount of time we will call backoff time. Okay, and after this waiting periods ends, it will start its transmission. Okay, now it's also possible that, let's say, the node decide to wait for 1 hour, okay, but the signal on the medium finishes in a half an hour. In that case, it will wait for an extra half an hour unnecessarily. Okay, so in the worst case scenario, using the same example, if nodes C and B are present and A and D are communicating with each other, so signal is already moving, then C and B will sense that the medium is busy. But as soon as transmission between A and D is over, the channel becomes free. Now what C do? When it first detect the medium is busy, it will wait for a random amount of time. Let's say C decide wait for 5 minutes, okay, and B decide for wait for 15 minutes, okay. So after 5 minutes, C will start its transmission. At that time, B will not transmit. So collision here compared to one persistent will be less. But if we talk about the optimal case, in normal situation where A and D were communicating, A stopped its transmission and C sees that the signal was moving, so it set its timer to wait for, let's say, 30 seconds or 30 minutes. It's possible that your channel becomes free much earlier, but you have set the timer to check the transmission capability 1 hour later. But it's possible that the very next second the medium becomes free. This means your transmission will obviously be delayed unnecessarily. So this is a problem in zero persistent CSMA, but collision compared to one persistent CSMA will be less. Okay, then we have P persistent CSMA. P persistence means P here represent a probability value. P persistence is actually a hybrid approach, a mixture of previous two approaches. Okay, in P persistence CSMA, it continuously check the medium like one persistence. Okay, if it doesn't find the medium idle, if the channel is busy, then it will sense continuously like one persistent CSMA. It keeps sensing continuously. Now let's say it detects the medium is free. After finding the medium free, it has a probability P that it will start its transmission. This means after finding the channel free, it will not transmit data immediately. Based on the probability value P, it will decide whether to start transmission or not. Okay, the value of P, generally the probability value is between 0 and 1, because if P is 0, then it becomes like 0 persistence, and its value is 1, then it becomes like 1 persistence. So P persistence uses the intermediate probability value. You can set the probability value as 0.5 or 0.1 or whatever you want. The concept of Wi-Fi generally uses P persistent CSMA. Now we are going to discuss CSMA CD, that is carrier sense multiple access with collision detection. We discussed CSMA in previous section. CSMA CD is a modification of CSMA, and the modification here is collision detection. Okay, this means here we can also detect when a collision occurs. The node which transmit data can also detect if its data has collided or not. Let me explain this. If I start data transmission and after some time my data collides with some other station data, how will I know that my data has collided or got corrupted? To find this out, we use the CSMA CD technique. Here many students ask whether we can use acknowledgement for this purpose. Let me address this concern. We are talking about acknowledgement in a scenario where we have 4 stations on shared media. Since we use CSMA CD in Ethernet technology, in LAN environment, if we use acknowledgement, then the overall collision rate will be increased significantly. The reason is simple. You are transmitting data and also sending acknowledgement, so your entire medium will be filled with both data and acknowledgement signals. Here data packets are already colliding with each other, and if you bring an extra functionality of acknowledgement, then collision will definitely increase a lot. So the first important point here is there is no acknowledgement in CSMA CD. This means the node which transmit data, let's say A start data transmission and after some time it data collides. If collision occur, then how will A know that it data collided? This is the fundamental concept of collision detections. Let's say we have 4 stations A, B, C and D, all connected with each other through shared media. Okay, so when A start data transmission, first it senses the medium like we discussed in CSMA. In CSMA, first it will sense, okay, and if the channel is idle, then it start transmission. Now when A start transmission, after some time D also start transmission. When D start transmission, the data from A and D collide at some point, okay, on the medium. Now data has collided. A is continuously sending the data, but A's data has collided. When data collides, such a frequency pattern is created, or the signal becomes corrupted in such a way that it has no validity. Okay, it becomes useless data. Here it doesn't know that its data has collided. It is continuously sending the data, but what benefit is there in sending this data? There is no benefit, because the data has already collided. So how will A know about the collision? A will know when A is transmitting data. At the same time, a collision signal comes back to it. This means I am transmitting data, and at the same time corrupted or collided data comes back to me. Okay, then A will understand that I am transmitting data and a collision signal is coming from the medium, so this means my data has collided. But if we consider that A's transmission has finished, meaning A has completed transmitting its data and is now idle, and some time later collided data comes to A, then A cannot judge whether it was their own data or like some other station data collided. Okay, because at this time A is not doing any transmissions. So only when you are actively transmitting and at the same time if your data collides and the collision signal comes back to you, only in this case will you know that it was your data, okay, that got collided. But if your transmission is already over and then you receive a collision signal, the station will not be able to determine this. The station might think that some other station's data got collided. Okay, so there is only one concept of collision detection when you are actively transmitting, and at the same time if you receive a collision signal, only then will you know that it was your data got collided. Okay, now let me explain this with a detailed example. Let's say we have a station A and station B. The propagation delay between A and B is 1 hour. If one bit starts from A and reaches B, it will take 1 hour. This is the propagation delay. Okay, now let's say at 12 p.m. A checks the signal. A senses the medium and find it empty. Okay, meaning idle. So it immediately start transmitting its data. When it start transmitting data, at the same time at 12 p.m. let's say B also senses the medium. What will B detect? B will also find that the channel is idle. Why? Because as I explained in CSMA, you can only check your own local point. So B will only check at its location if there is a signal present but no signal from A has reached B yet. So B will also decide to transmit data. Now what will happen? After exactly half an hour, both of their data will collide. When both data packets collide, corrupted data with a new frequency pattern which is useless will propagate in both direction. Okay, but when will that collision signal reach A? When the collision occurs at 12:30 p.m., the collision signal will reach A after another half an hour. So at 1 p.m. both A and B will receive the collision signal. Now after 1 hour they will know that their data has collided. Both data packets came into collision, but the important condition here is that the A should still be transmitting at that time and B should still be transmitting at that time. They should be transmitting until 1 p.m. Then they will know that it was their data collided. Okay, if they are still transmitting when they receive the collision signal, then they will know that it was their data came into collision. From this example, one fundamental rule can be understood. Transmission time should be greater than or equal to 2 times of propagation delay. Why? Let me explain it with worst case. In worst case scenario, let's say A's data collided at 12:59 p.m. At exact 12:59 p.m., B senses the point and it was idle and it started transmitting data. So what will happen? A collision will occur here and the collision signal will reach A at 2 p.m. because propagation time is 1 hour between A and B. A will know that its data came into collision, but this is only valid under the condition that A is still transmitting at that time. If A stopped transmitting at 12:05 or 12:10 or 12:30, 1 p.m. or any time before 2 p.m., then it cannot detect the collision. So in the worst case, how long should the transmission time be? Transmission time should be greater than or equal to 2 times of propagation delay. This is a very important formula. Transmission time is greater than equal to 2 times propagation delay. Now if we extend this formula, transmission time equal to message length upon bandwidth. Okay, so it will be message length upon bandwidth greater than equal to 2 into propagation delay. Then length equals to 2 into propagation time into bandwidth. Okay, minimum frame size should be equal to 2 into propagation delay into bandwidth. Okay, now if we talk about efficiency in CSMA CD, efficiency eta equal to 1 upon 1 plus 6.44 A. Okay, where A is propagation delay upon transmission time. This is the whole concept of CSMA CD. Now I am going to explain CSMA CA, that is carrier sense multiple access with collision avoidance. If we are talking about CSMA CA, where do we use it? We use it in wireless lane. Okay, you can call it Wi-Fi or IEEE 802.11 standard. So here we use CSMA CA, carrier sense multiple access with collision avoidance. So remember, collision detection is used in wired network and collision avoidance is used in wireless technology. Okay, what happens in wireless network is different. Okay, when your data signal is transmitted wirelessly, as it travels through the air, it loses energy due to various factors like distance, obstacles or interference, etc. Okay, due to this energy loss, the receiving station will not get the double energy signal that is needed for collision detection. Unless it gets a significantly higher energy signal, it cannot detect that there is a collision. That's why in wireless networks we use collision avoidance instead of collision detection. Now I will explain the complete strategy of CSMA CA with this flowchart. Step 1. Initial step, when some station want to start transmission, initially the value of k is 0. K represents the number of attempts. When a station comes for the first time, the value of k at start is 0. Carrier sensing first. Step 2 is carrier sensing first. What does it do? It senses the medium because it is CSMA. Okay, it will first sense the carrier. It checks is the medium idle or not. If yes, it proceeds to next step. Okay, if no, then it go back to sensing again. Okay, it will sense again until it gets the idle medium. Step 3, interframe space, IFS. Wait when it finds the medium idle. What does it have to do? It has to wait. Here we never do data transfer directly. Okay, the concept of waiting is most important in CSMA CA. So what will it do? It waits for IFS, interframe space. Why does it wait? It waits because maybe some other station has already started transmission. So to prevent future collisions, even though it detected the medium is idle, it knows this only as its own location. Okay, in the entire network domain, it cannot know if the whole domain is idle or not. It can only see at its own end and that there is idle space, but it doesn't start immediately. Okay, it waits thinking that maybe someone else started transmission. Step 4 is contention window after the IFS wait. Here it choose a random number r between 0 to 2 power k minus 1. Let's say it's the first attempt, so k equal to 0. Then the range will be 0 to 2 power 0 minus 1 equal to 0 to 1 minus 1 equal to 0. Okay, so it chooses 0, meaning it doesn't wait additional time. Okay, if a collision occur and it tries again, k becomes 1, then the range becomes 0 to 2 power 1 minus 1, okay, equal to 0 to 1. So it will choose either 0 or 1. After the next collision, k becomes 2 and the range becomes 0 to 2 power 2 minus 1 or equal to 0 to 3, then 0 to 7 and so on. This value keeps growing exponentially, okay, with each collision. Okay, step 5 is slot time wait. The chosen random number represents slots. Okay, each slot has a fixed time duration, let's say 5 seconds per slot. If it choose 0, it will wait 0 slots, no additional wait. If it choose once, it will wait 1 slot, 5 seconds. Okay, if it choose 3, it will wait 3 slots, 15 seconds. This contention window makes the station wait more, reducing the probability of simultaneous transmission. Okay, step 6 is RTS, ready to send. After the waiting period, it sends an RTS, ready to send signal. Okay, this is not the actual data yet, just the signal indicating I am ready to send data. Okay, step 7 is what? Short IFS wait after sending RTS. Okay, it waits for short IFS, SIFS, a short waiting period. Why does it wait? Because it doesn't have a clear confirmation yet. CTS, clear to send. Step 8, okay, the RTS signal goes to the access point like a modem or router in a Wi-Fi. The access point responds with a CTS, clear to send signal, if the medium is available. Okay, step 9 is final wait before data transmission. Even after receiving CTS, it waits again. Why? When the access point receive RTS, it immediately stop all transmission, signaling stop, someone is sending to send. Okay, but it's possible that some just before this RTS signal someone else started transmission, so it waits again as a safety measure. Step 10 is data transmission. Finally, okay, it transmits the actual data frame. Step 11, acknowledgement after sending data. Okay, if it waits for an acknowledgement. If acknowledgement is received before timeout, then success. If acknowledgement is not received, then there was a collision. Okay, step 12, collision handling. If there is a collision, no acknowledgement received, okay, that the value of k increases by 1 and it goes back to the contention window phase. Okay, if the number of attempt is less than the limit, it continues trying. Okay, if it exceeds the limit, the transmission is aborted. And step 13, backoff time. The backoff time TB is calculated as TB equal to R into slot time, where R is the random number chosen in the contention window. Okay, the slot time is generally equal to the round trip time. Okay, this whole concept was CSMA CA, collision avoidance. Okay, and this was whole CSMA. So that's it for this video. We will meet in next video. Until then, bye bye.